Hi, this is going to be a quick summary of Chapter 1. This is on page 72 in your book if you want to look at paper of this or have a reference to it, which at the end of every chapter there's a pretty good summary of all the main points and concepts that you need to go through. And where they start out in this book is they start talking about algebraic expressions right here, which is basically something in algebra language is what they're talking about. And algebra is made up of numbers and operations like addition, subtraction, multiplication, division, exponents, powers, which is really multiple multiplications, and so on. Well, and also we bring in this idea of a variable, so we can have a letter represent some value we don't know yet, which helps us to set up a way to solve more complex word problems, or basically problems that are in English, in our case in this language, and translate them into algebra, because algebra is really a language. So we're going to focus in on the words, and it's very important not to disregard this, is to pay attention. These words are used all the time to explain things and ask things. So if they're looking for you to evaluate an algebraic expression, that means something very specific, and this is what this example is about. So like in this case, this example is x plus y, these variables that we could put any values in for x and y all over 8. So this is a fraction, and if they want us to evaluate it for when x is equal to 15 and y is equal to 9, well, you put those values in for the variables. Remember, got to use order of operations, and what's sometimes a mistake that happens is a fraction bar creates a grouping of the numerator and the denominator. So this 15 plus 9 is really in grouping symbols, so it becomes that operation needs to be performed before the division of 8. And the value they're talking about is, what is the value of this expression when you substitute in these values to evaluate. Okay? And we use that like in formulas for area of a triangle and so on. As we evaluate that, this is really an equation, has an equal signs in it, where area is equal to 1/2 the base times the height. And if they give us the base and the height in 3.1 meters and 6 meters, we put that in here. Now notice that they keep the meters as label as is a value, and then they're going to actually use the commutative law and the associative law, which we'll talk about here a little bit, which allows us to change the order of a multiplication and the grouping of it, and actually come out with this as meters squared, because that's what area is measured in squares. So this is pretty key note here to help with some things coming down the road too. So if they give us the base and height, we can come out with an area here like 9.3 meters squared, or square meters. And that's what we're trying to do, is get so we can translate phrases from English to algebra. So we can translate in a word problem, we can translate it to an equation in this case by using algebraic expressions and knowing the keywords for equal and so on. In this section in the book, and the main details, I think there's a whole page on translating English to algebra, like is means equals, and are, and some other things. Difference means subtraction. Product is the answer to a multiplication. Factors, we're going to talk a lot about, are parts of a multiplication, and so on. There's a lot of words to know. You should study that while you're working on this. And also a little bit of strategy that will come up a lot at different times. But when I'm translating something here, especially with subtraction, order matters. We're going to talk about the commutative law. You can kind of see that here. If I jump down here a little bit, the commutative law means I can change order and get the same result, but it only works on addition and multiplication. It does not work on subtraction. So when it says when 34 is subtracted from a number, the result is 13, what is the number? They translate this to 34 subtracted from a number. And that's probably why they use n, because they got this word number. But you could use x and so on. A lot of times I'll go back and reread it with the variable in there. It helps write it sometimes. 34 is subtracted from n. And now the mistake that happens from that translation, especially with subtraction, is to go 34 minus n. Now I'll throw some numbers in there and see if it works. This is called solving a simpler problem. What if I said 34 subtracted from 100? Would I go 34 minus 100 to get 66, right? No, you would go 100 minus 34. By doing that, that's an outstanding strategy in all problem solving, is to do a simple problem. Throw a number in there and see if it works. And in this case, actually, you could, figure it out. And then bring it back, because you can solve this equation and find out what number they're talking about, and then put it back and see if it works in the original. But here they're just focusing in on this translation. Section 2, they get into these three very important laws: the commutative, associative, and distributive law. The commutative, and use these words, please. When you're working on this and you're actually doing some of these problems, think about the whys you're doing that. If you looked in the examples in the book, they'll have red type to the right of it, and it's explaining which laws were used to do each step. Okay. So here it is in algebraic language, which is important. Get used to that. Get focused in on really understanding what that means. And here's some actual examples with numbers. The associative law allows me to change the grouping. If I have A plus the quantity B plus C. Now remember, order of operations would force me to add B and C before A here. And here I'd have to add A and B before I add C, and so on. Like in this example, if I did this side, I'd end up with negative 5 plus 11. If I did it on this side, which is a very good example, because by grouping, being able to change the grouping, I can add negative 5 and 5 together, and that's 0. So I get 0 plus 6. You'll end up, that's a lot easier math to do. You'll make less errors. Same thing with this multiplication. On this way, I'd have to do what's in the grouping symbol first, so I get 5 times 9, which is 45. Then I'd take it times 2, and I'd get 90. I would much rather do it this way and take 2 times 5 is 10, and then 10 times 9 is 90. It's just a lot easier way to do it in your head. So it has value, a lot of value. In fact, without these two laws and this third one, we would be stuck on doing a lot of algebra because of order of operations. In other words, these laws can override order of operations by changing the grouping symbol, changing the order of things when we need to. The distributive law allows me to deal with multiplication over an addition of a group. So if I have A times this quantity, B plus C, I can rewrite that as A times the first part of the addition plus A times the second part of that addition. And they show it here. If I was going to multiply 3 times 2x plus 5y, I can multiply 3 times the 2x and then multiply 3 times 5y, and I'd end up with this new algebraic expression, 6x plus 15y. Now when I factor means by using the distributive property, if I have a common multiple of each one of these parts of the addition, which is, I'll notice that this is 8 times 2, this is 8 times 3, and this is 8 times 1. I can factor out, or basically pull out, a multiplication times each one of these terms and say this is 8 times the quantity 2x plus 3y plus 1. Going back to the way we're probably used to seeing the distributive, if I distribute that multiplication of 8 over these 3 different add-ins or parts of the addition, I'll end up with the original. Then they get into fraction notation, and the first thing they do is they go into what a prime number is. Notice this black type means that it's a defined word. It's going to be important that you understand exactly what that word means, and here's the exact definition of a prime number. It exactly has 2 factors. Now, if you don't remember what a factor is, that doesn't do you much good. But factors are parts of multiplication. So, definition of prime number has exactly 2 factors. So, this first examples are some of the first primes or smaller primes. 2 is prime because if factors of 2, what I'm really asking for, what numbers can I multiply together to get this product? Product means the answer to the multiplication. In this case, the product of 2. Well, 1 times 2 is 2, and that's it. There's no other numbers I can multiply together to get 2. That means that 2 is prime and has exactly 2 factors. Now 4, I can take 1 times 4. There's 2 factors. And I can also take 2 times 2 and get 4. So I have 3 factors. Or if I have more than 2 factors, it's a composite number. Now this is about fraction notation, and they're doing this. This is going to be a tool that we use to help us with fraction notation. And then they say, well, we can do a thing called prime factorization. In fact, there's a rule that says there's exactly every number has a unique prime factorization. So I can write every number as a unique multiplication of prime numbers. So this example is showing us is 136. We can break that into 2 times 2 times 2 times 17. Notice that all 4 numbers are prime, and that would be a prime factorization of 136. You'll see trees used, factorization trees, which is a good tool to use. But while we're doing this is really what's setting up for fractions. Then they tell us that if I have a numerator and a denominator that are exactly the same, that's equal to 1. I don't think that's going to be any big revelation to anybody. But there must be a reason that they're really pointing this out at this point. And they show examples of that. Hey, 15 over 15. They're the same thing on the top and the bottom, the numerator, denominator. It's equal to 1 by definition. If I have 2x over 2x, by this definition, it has to be equal to 1. But there's also one other condition. You've got to make sure that x is not 0, because we can't divide by 0, or denominator can't be 0. It's undefined. In fact, this number 1, created by this definition of a fraction, is so important they actually name a property of 1, the identity property of 1, which is that I can multiply anything times 1 and I get that same thing back. So if I do things like this, and this is exactly where we're going to work with fractions, with multiplication and addition, 2/3 is equal to 2/3 times 5 over 5. It says since 5 over 5 is 1. So based on this, because I'm multiplying by 1 in this special way, I know that this next fraction I get on this side, which would be 10 over 15, is equal to 2/3. In other words, there really is an infinity of ways I could write 2/3. And this fraction is in simplest form, which has a real distinct definition. But I can write an infinity of fractions that's equal to 2/3 by doing basically multiplications by 1 by using fractions equal to 1. You know, if this was 4 over 4, I'd say it's 8 over 12 is the same as 2/3. And so on. I could keep going. But they're pointing out that this is possible, and this works because of these rules that they just gave us. And in fact, this is, number 1 is called the multiplicative identity, or the identity a lot of times for multiplication, identity property 1. a lot of different kinds of words, but that identity is always consistent. Then they give us the rules of addition, subtraction, and multiplication and division. You need to be very comfortable. I see a lot of students are not real comfortable about working with fractions. If that's you, spend some time in section 3. You need to get so you understand exactly what's going on when they work with this. Also, I don't think they show it here, but what simplest form means is that the least common, or the GCF, the greatest common factor between the numerator and the denominator, there's that factor word again, is 1. So the GCF, greatest common factor of the numerator and denominator, is 1. So what are the factors of 2? Well, it's 1 and 2. In fact, it's a prime number. What are the factors of 3? 1 and 3. The only common factor they have is 1. In other words, that's the greatest common factor. This fraction is in simplest form. And why I'm bringing that up is that when we get into multiplying, they always expect the fractions to come out in the simplest form. But first, we can do things like they're kind of doing multiplication. You got to remember that they do multiplication here too. They don't perform that. But when you multiply, you take numerator times numerator, denominator times denominator. And that's what they're showing right here. Here it is in algebraic notation. And get used to this. If you just really think about, I have A, B, C, and D, which can be any numbers. This A is the same as that A. So if I put these values in here, and if I multiply two fractions, it's really the same as taking numerator times numerator, A times C, over denominator times denominator, B over D. When I divide, I change it to a multiplication. And what you're really doing is taking the divisor, the part that's being divided by, which in this case is C over D, is you invert that or take the reciprocal of it and multiply. And then you apply the rules of multiplication. So you need to know how to do, especially this multiplication, before we look at this example for addition. Now addition, if you have exactly the same denominator, which you need to have before you can add the numerators. And if you think about this with pizza or something like that, if I have 3 out of 6 pieces and 2 out of 6 pieces, if they're the same size pieces of pizza, I would end up with 2 plus 3 or 5, 6. Now if they're not the same, that wouldn't make any sense. If I had a pizza that was split into 6 and I had another one that was split into thirds, and I said I had 3 pieces, you would need to know which size pizza I'm talking about, right? So the size of it really matters. So what we do to do addition of fractions, we have to get a common denominator where we have 1/6 plus 3/8. They rewrote 4/24. What they really did is first figured out that we needed the least common multiple of 6 and 8 is 24. So in other words, if I take 4 times 6, I get 24, and if I take 3 times 8, I get 24. And that's exactly what they did here, is they really took 1/6 and multiplied it by 4 over 4, like they did up here, right? 1/6 times 4 over 4. Why can they do that and it won't change the value? Because they're really multiplying by 1. You get 1 times 4 is 4, 6 times 4 is 24. You get 4 24s. Now this fraction I'd multiply times 3 over 3 and get 9 24s. Why? Because I got to get that common denominator. And then once they're the same denominator, I add the numerators and get 13. Then I check to make sure it's in simplest form. Well, exactly the same thing happens for subtraction. And here they actually show the multiplication to get the common multiple. They say, well, if you have 5/12, right, minus 1/6, they take 5/12 minus 2/12, which is 3/12. And then what they do is they say, 3/12 is really 1 times 3, and 12 is 4 times 3. Why did they break that out that way? Well, 3 over 3 is 1. In other words, they're simplifying the fraction 3/12 to be 1/4. They're actually the same position on a number line. They're equal. Big deal. Big deal about fractions. We will use that. You might have a whole bunch of stuff you know how to memorize, or you're using your calculators for fractions. Well, as soon as I start sticking variables in there, you're going to be in trouble. You won't have any way to stick that in your calculator. You're going to have to understand this process of using factoring and fractions that are equal to 1. Section 4 is about positive and negative real numbers. And they define our number sets, which is important because we actually bring back, when we're talking about exponents, different chapters in this course, you're going to need to know what integers are and those kind of things, because they're going to say that they're going to use that in definitions. So the natural numbers, and kind of where they start here is that that's our counting numbers. They used to think that, and they still do, I think, with children, the idea of an abstract concept. If you think about grade school or kindergarten, when you were starting to learn how to count and stuff, if you remember that, they had blocks and things that you could actually hold and see. You could put them into different groups and count them and all that kind of stuff. Well, the idea of 0 isn't defined there very well. That's really an abstract thought. And they have the whole number set. And we do use natural numbers for certain things when we're defining. The whole numbers are the naturals with this set notation, this little squiggly bracket, is a set of 1, 2, 3, 4, and so on. It continues. That's kind of the way to describe that set. But they need to find a way to deal with infinity, because there's really an infinite number of natural numbers that counts up forever. Goes to infinity. How do we put a wrapper on infinity? So they're starting to define a set notation to basically say, there's more in here. And we're going to be able to have some ways to show pictures of that or draw a set notation to describe it more easily. Whole numbers, integers are all the whole numbers and their opposites or additive inverses or a -1 times that. You'll hear me say those 3 statements over and over together a lot of times when I'm teaching classes. So, because they all mean the same thing. 1's opposite is -1, which means it's the same distance from 0 on a number line on the other side of it. Or it's additive inverse, which means if I add -1 and 1 together, I get 0, which is the identity of addition. There's that word identity again. Or it's a -1. If I take 1 and take it times -1, you get -1. If I take -3, I want its opposite. I take it times -1, I'll get +3, and so on. Now, rational numbers are in this set notation. I'm going to go through exactly what this says and then put it more into English. There's that set notation. It says A over B such that this bar pipe symbol is such that A and B are integers in this number set here, and B is not equal to 0. So in other words, rational numbers are numbers I can write as fractions using integers as numerator denominator. Okay? Now, except B cannot be equal to 0. I can't divide by 0. What is division? Division is multiple subtractions. So if I thought I could divide by 0 and I said 4 divided by 0, what I'm really asking is how many times can I subtract 0 from 4 to get to 0? Well, I keep subtracting 4s. I wouldn't get any closer to 0. It just doesn't make any sense, so it's undefined. Now, irrational numbers are numbers that I can't write this way, and there's a lot of them. So if we can't write it as a fraction of 2 integers, I end up with something called irrational, which means not rational numbers, like the square root of 7. There's no way I can write that as a fraction. We have this pi symbol, which is has a bunch of estimates we use. Pi is generated. Really, this is the diameter of a circumference of a circle divided by its diameter. You get this pi, that ratio that occurs, though I never found an exact value for. It's about 22/7, but that's an estimate. And then they say, well, for every rational number that can be written as using fraction notation or decimal notation. Well, really, decimal notation is just fractions, isn't it? Here's the tenths place, the hundredths place, the thousandths place, 10,000ths. This really means 625, a negative 625 over 1,000. And they say it's a terminating decimal. Excuse me. Because it ends up with, really, I would argue with the books a little bit. What ends up, if you actually do long division, there's a zero here. In fact, a lot of times we throw zeros on there to say write this as a fraction using millionths or something like that. I can always put zeros on it. In fact, there is a repeating zero that goes on all the time. Now with 5, 6, if you take 5 divided by 6 on your calculator, you're going to get 0.833333333, and then it's going to be the end of your display. You could probably recognize that the 3 seems to be repeating. And how we deal with that is to put a bar over that 3. And what we do in this class is write it as a fraction. That's the accurate way to do this. Because if I write 8.3333, if I write what's on display of your calculator, you have basically written an approximation of that. It's not the exact value, and so on. But this is what they mean by repeating decimals. They're still rational because this is an integer over an integer. Now, for every real number on a point on a number line, this is an outstanding tool that you should probably get very used to drawing on your scratch paper. Is anytime you can draw a picture of something in algebra or math, you should do that. Well, we have a set way of drawing pictures, which is you draw this line, you put these little arrows here. In fact, these little arrows kind of look like these inequality symbols, don't they? And we'll talk about that. But you have a way to basically draw a picture of a numbers in a system. And what they're doing here is kind of showing you that, the square root of 2 is an irrational number, but it actually has a given point on a number line. We just don't have the ability to get the exact location. We can get infinitely close to it, but we're not quite sure exactly where it is. But it exists between 1 and 2, definitely. And then they show us some things about inequalities, greater than, less than. Well, one way to read this, 4 is greater than negative 3.1. But this symbol comes from this little arrow marker. It means 4 is right of, on a number line, negative 3.1. And it is, isn't it? That's true. Now, if I flip that around and I said negative 3.1 compared to 4, well, I'd say, well, negative 3.1 is left of, or less than, 4. Okay? And here they show half compared to square root of 2. 1/2 is left of square root of 2. If I had square root of 2 on this side, it'd be square root of 2 is greater than negative 1/2. So on. Then absolute value, here's some of these things are darker type. These are important. Absolute value means distance from 0. And the way they write this, they say it's a number of units that the number is from 0 on a number line. Okay? So if I have these pipe symbols on each side of something, it means the absolute value of, well, how far is 3 from 0? It's 3. How far is negative 3 from 0? The absolute value of negative 3 is 3. So on. It's not necessarily turn it positive, and when we get into more complex algebra, you need to know the definition, distance from 0. Section 5, we're going to add real numbers, and we can do that in any order. The way I'd like to think about this is to draw a number line. Like when I'm adding two negatives, and it isn't too hard to go, you go 8 to the left is 0, and then another 3 to the left, and you end up at negative 11. Well, if I use that number line idea, I don't have to know all these rules about when I have opposite sign add-ins. They talk about absolute values, which is good to know, but what I would go is I'd go 8 to the left is 0, then 3 to the right, and I go, I'm going to stay on the left side of 0, so it's negative, and I'm going to end up at negative 5, and so on. Okay? And they also show additive inverses, or adding opposites, or adding the number that is negative 1 times it, and you always end up with 0. And that's where this identity property becomes important, is if anything I add 0 to it, just brings back that same value. That's what the algebraic expression here, they show 2 examples. Then subtracting real numbers. Here's that opposite or additive inverse is defined. And I would say the other way to describe this is really when they put a negative in front of something, it really means negative 1 times it. And I'll bring that up a bunch of times at different times to alleviate sign errors. I'll hear students say, well, it's just a sign problem. That is a huge deal. It is not a minor thing. There's a big difference between making $100 and saying you got 100. And if you said I made a negative 100, I would think that you lost $100. So there is a big deal. So they show the different things that can happen here. We see when I need to evaluate like a negative number when it's negative x, think about the x as being a slot that you put that negative value in, and you got the negative of a negative 1, which is really negative 1 times negative 11, and which is a positive 11, and so on. When we subtract two real numbers, the opposite number, we add the opposite number being subtracted. In other words, they're giving a way to get rid of subtraction. I can change everything to an addition, which has huge advantages because now I can use the commutative property and the associative property by changing subtractions to addition. So if I had negative 10 minus 12, I would go, when I think about it in addition form, I go 10 to the left of 0 and then another 12 left of 0, and I end up at negative 22. When I see these kinds of things, I see all kinds of errors. So when I say, like this one is a very good example. I throw this on the board a lot of times. I say, what's the answer? I get a lot of people say negative 3. And really it is 15. Because when I change this to a multiplication, that's what I go and I say, well, you're telling me 6 plus 9 is negative 3. That doesn't make sense, right? Because you add its opposite, or add the negative 1 times it. Okay? Or add its additive inverse. The opposite of negative 9 is 9. The additive inverse of negative 9 is 9. Negative 1 times negative 9 is 9. They all end up doing exactly the same thing. In fact, I like the negative 1 times it because algebraically that is purely in the language of algebra, which is where we're trying to get to. So they tell us how to change subtraction to an addition, and then they get into terms. Terms are parts that are added. And what's important to note here, like this expression, negative 2x plus 3y plus 5x minus 7y. Notice that the term here is for this one where I'm subtracting is negative 7y. In other words, they treat this as if it was changed to an addition, because by definition, terms are parts of an addition. Okay? So we end up with the term being negative 7. And they'll ask us, what are the terms? So you need to know what the word means. And then like terms can be combined, which is using the distributive property and factoring to do that. Then multiplication, division of real numbers. is, and then there's that division is undefined by 0. Well, if I have negative times negative, I get positive, and positive times negative, I get negative, whether it's multiplication or division. And once we get to this multiplication, then I start seeing errors here. Is when I see this a lot of times, or those kinds of things will get errors. You start wondering, trying to apply these rules to an addition. When you're in addition, think of a number line. Then they get into exponential notation, which is using exponents. Exponents are really have two parts to it, a base and an exponent. We've been using this notation on our number system, a base 10 number system that we have, which is everything, every place is some 10 to some exponent. Like you have the tens place, hundreds place is 10 to the 2 power, thousands place is 10 to the third, and so on. But what this means is, in this notation, it means that the base is a factor n amount of times. So here there are factors, parts of a multiplication. And how do we know how many of those multiplications occur? We make sure the count equals this exponent. So if I have 6 to the 2 power, that really means 6 is a factor twice, and I get 36. If I have negative 2, notice the grouping symbols here, and this is really a lot of errors around this, means negative 6 times negative 6, which is positive 36. If I have the negative of 6 to the 2 power, or negative 6 to the 2 power, I really should say the negative of 6 to the 2 power, means that order of operations, if you think about that negative, is really negative 1 times something. So another way to write this is negative 1 times 6 to the 2 power, where I take the negative of 6 being a factor twice, and I end up with negative 36. And then they show it with variables. 6x really is just 6 times x. There's a lot of the laws they could have shown here. I could have said, well, I could change the order of this multiplication. This is really 6 times x times 6 times x. I could change the order to be 6 times 6 times x times x. I could group them using the associative law and group the 6 times 6 and the x times x and end up with 36 times x to the 2 power x squared. And then they bring in order of operations, which is PEMDAS. Look that up. The opposite of a sum for any real numbers is that they really want us to see, if I take the opposite of anything, a sum or a difference or whatever we're talking about, it's really negative 1 times it. If I go to the distributive property and consider this negative 1 of this grouping 2x minus 3y, it really means negative 1 times that. I would distribute. I take negative 1 times 2x, which is negative 2x. Then I would take negative 1 times negative 3y and get a positive 3y. Okay? And you'd end up with that right there, right? You take negative 1 times 3y, you get a negative 3y. And then you subtract that, you change it to an addition, you get positive 3y. And then the last part is simplifying, or expressions containing parentheses, and simplify by removing parentheses using the distributive property, which is factoring, or I multiply. And then afterwards I'm going to look for things that I can actually add together, like adding like terms, which is really having factors, being able to factor out the number portion or coefficients in a way that I can actually perform an addition. And that's it for chapter 1.